Hello everyone, welcome to the next lecture which will be on applications of Schrodinger equation, and we are going to consider the case of infinite potential well. Before moving ahead with the mathematical forms, let's first understand the scenario. So what we have is a kind of structure which is looks like a well, a typical well, okay? And say it has a width of maximum size L. That means I can consider the width for the x-axis, x is equal to 0 to x is equal to L. And the y-axis is the potential energy, and which goes from 0 to infinity. Well, so we have actually considered an open well. So the reason, so we don't have it closed over here on the top. So the potential energy at the maximum, it can go till infinity. So that's the reason it's called as an infinite potential well. Now, what are we going to do? We consider a particle inside this potential well. Now, while looking at this figure itself, you can understand that the particle will be free to move inside this well, but the moment it is at the boundary, it is not able to cross, be it on this left hand side at x is equal to 0 or at x is equal to L on the right hand side. So the particle is free to move inside, but it is not free to move at the boundary. So there is a limitation. Now, just for your reference, this condition is also referred to as a particle existing in an infinite potential well, or a particle in an infinite potential box. This is like an open box also. Now, so what are we going to consider? First situation, when the particle is inside the well, it is free to move. When something is free to move, that means there is no force acting on it. If the force acting on it is 0, then we know that force is negative gradient of potential. F is equal to minus del V, or F is equal to minus d by dx of the potential energy. So if F has to be 0, then potential energy has to be a constant. Then only the gradient will be 0. Potential energy has to be constant, and let us consider that constant value as 0. Okay, let's consider the minimum potential energy value which will be 0, the constant value as 0. Now, what are we going to do is bring in Schrodinger's equation of motion, apply the condition that potential energy will be 0. Then I can rewrite the Schrodinger equation. This is a time independent Schrodinger equation. I can rewrite it as d square psi by dx square plus 2m by h cross square into E into psi is equal to 0. So your Schrodinger equation had E minus V of x. Now V of x, the potential energy V is 0. So for that reason, it just becomes 2me by h cross square into psi is equal to 0. So if you remember from the previous lecture on quantum mechanics, so we had derived the Schrodinger equation, and we told that the Schrodinger equation can be solved to find the eigenfunction and the eigenvalue. Our aim is also the same. We bring in this particular situation of a particle which is existing in an infinite potential well. We apply it to the Schrodinger equation, solve the Schrodinger equation, get an expression for the eigenfunction, and get an expression for the eigenvalue. Now, eigenfunction will be nothing but the solutions of this equation, that is this wave function psi, and eigenvalue will be the energy values at which the wave equation will be valid. So in order to solve this, let's consider 2me by h cross square as another term k square. Now k here is actually called as the wave vector. Moving on, so I can replace 2me by h cross square with k square. The equation can be rewritten as d square psi by dx square plus k square psi is equal to 0. So this is now in a better form which can be solved, and the solution will be something like this. Psi of x is equal to a constant a into e to the power of I kx plus b into e to the power of minus I kx. A and b are constants. Now we need to, if the solution is not sufficient, we need to solve A and B and get a better form for the wave function psi of x. In order to do that, let's bring in the boundary conditions. So what are the boundary conditions? If I go back to the figure here, I know the particle cannot cross this boundary. Particle cannot cross the boundary means the particle is not existing or after this boundary, or the wave function becomes zero. Its probability obviously is zero. The particle doesn't even exist. So at the boundary, that is at x is equal to 0 and x is equal to L, the wave function becomes 0. So let's apply the boundary condition now one by one. First, let's consider at x is equal to 0, wave function is equal to 0. So I can, from this equation, I can write it as a plus b is equal to 0, or I can take b is equal to minus a. Put this b is equal to minus a back into the solution of psi of x. You will get psi of x is equal to a into e to the power of ikx minus a e to the power of minus ikx. We replace b with minus a. Now a is common, so I can take it out and put in bracket e to the power of ikx minus e to the power of minus ikx. Further, e to the power of ikx minus e to the power of minus ikx divided by 2i is nothing but sine of kx. So this representation we can make use of. So instead of e to the power of ikx minus e to the power of minus ikx, I can write sine kx into 2i or 2i sine kx. Putting it back, I'll get psi of x as psi of x is equal to a into 2i sine of kx, or 2ia into sine of kx. Moving on with the next condition, that is when x is equal to L, wave function becomes 0. So in the previous equation, I have psi of x is equal to 2ia sine kx. Now I can make x as L. So 0 is equal to, wave function should be 0 at x is equal to L. So 0 is equal to 2ia into sine of kl, or 2 constant I, constant A, constant. Constants cannot become 0. So what has to become 0? It has to be sine of kl. Sine of kl will be 0 whenever kl is an integral multiple of pi. 0, pi, 2 pi, 3 pi, 4 pi, like that. So kl is equal to n pi. Now the wave vector k is given by 2 pi by lambda, where lambda is the wavelength of that wave. So I can write lambda as 2 pi by k and substitute for k over here. So kl is equal to n pi, so k is n pi by L. I substitute it here, I get an expression for lambda, that is 2L by n, and for obviously n is equal to 1, 2, 3, 4, etc. Now, what are we going to do next? So one point to be noticed here is that, so wavelengths here, lambda, for every n, it is, you're going to get a constant value. So because of that, it forms a standing wave. It forms a standing wave. Wavelength will be discrete quantity. The wavelength will be in discrete. So 2L by n, sorry for that, 2L by n, 2L by 1, 2L by 2, 2L by 3, 2L by 4, like that. Each of them for every n is a discrete quantity. So it forms a standing wave. It forms standing wave. Now, momentum P I can write as h cross into k. H cross into k, or h by 2 pi into k. So this is a pretty simple expression, this which comes from de Broglie's expression, that is lambda is equal to h by p, and you have p will be h by lambda by 2 pi, multiply and divide by 2 pi, replace 2 pi by lambda with k, so it becomes k over here, and h by 2 pi remains there. So h by 2 pi into k, or h cross k, we call it as. Now k is n pi by L, we just now got it, substitute it, you get it as nh by 2L. So you got momentum as nh by 2L, then it is pretty easy to find the energy of the particle, which is having a mass m, that is p square by 2m. Substitute for p, you will get n square h square divided by 2m into 4L square. So it becomes n square h square by 8m L square. This is the expression for the energy values of the particle at different values of n. N is equal to 1, it becomes E is equal to 1 square h square by 8m L square or h square by 8m L square. N is equal to 2, it is 2 square h square by 8m L square. N is equal to 3, it's 3 square h square by 8m L square. That means for each n you have a different value of the energy, or energy now is a discrete quantity or it is quantized. So for each n there will be a different value of the energy. So this n is equal to 1, this point, this level corresponds to energy level 1, n is equal to 2 will be E2, n is equal to 3 will be E3, like that and so on. Now I have shown in this figure the wave function form. So how do we get this form? That is what we look into next. So our aim, as said earlier, is to find an expression for the energy values. That's the eigenvalue. We have got it, n square h square by 8m L square. And next one is to find the eigenfunction. For that, let's go back to this expression which we got, psi is equal to 2ia sine kx. I will replace 2ia because all of them are constant. I can, whatever is their product will also be a constant. I will replace it as c. So c into sine of kx. Now total probability should be 1, or in another way I can normalize the wave function, right? So integral psi into psi star dx is equal to integral mod psi square dx is equal to 1. So in the next step, substitute for psi and psi star. So integral c into sine kx, psi star will be c star sine star kx dx equal to 1. C, I'm just going to rewrite it. C into C star sine kx into sine star kx, integral over dx will give you 1. Or integral of mod C square. So C into C star becomes mod C square, and sine star is nothing but sine itself. So sine into sine star becomes sine square kx, sine into sine or sine square kx. So integral mod C square sine square kx dx is equal to 1. Now, I can take out mod c square because it doesn't have any dependency on x. Mod c square into integral x, and sine square kx I can write as 1 minus cos of 2 kx by 2. There is sine square theta is 1 minus cos 2 theta by 2 in the same form. I'm going to write it. Multiplied by dx, integral over x will give you 1. Now, this needs to be solved. Whatever is there within the integral. Right now I've written it in terms of x. I'm going to bring it in terms of L. So how do we do that? I put the limits for x. That is mod c square remains as it is outside the integral. Then multiplied by the integral, limit going from x is equal to 0 to x is equal to L. 1 minus cos of, instead of k, I'm going to write it as n pi by L. So 2 n pi by L into x whole divided by 2 into dx is equal to 1. All we did is replace k with n pi by L. Let's solve this. So we need to split up these two terms over here. So mod c square and fully multiplied by what? Integral 0 to L half dx, that's the first term, minus integral 0 to L half cos of 2 n pi x by L into dx, all of them equal to 1. Now, obviously the first term within the bracket, it is pretty easy to solve, but not the second term, right? So what are we going to do is, we are going to take 2 n pi x by L as another term u. So then I can write du will be 2 n pi by L into dx. When x is equal to 0, one more thing, when x is equal to 0, u will become 0. When x is equal to L, u will become 2 n pi. So I'm just bringing it into another variable in order to solve that expression. So I get mod c square into, so I solve the first part, that was integral half dx, and put the limit 0 to L. I get L by 2 minus half Now this integral is going to be in terms of u. So it becomes the integral u is equal to 0 to 2n pi. We notice that the limits have changed now. Then cos of u, because it was 2n pi by x by l. So cos of u. And du we have, but we have to write dx. We need to replace dx. So it becomes L by 2n pi into du. In the next step, mod c square into L by 2 minus, let me take out this L by 2n pi outside. So L divided by 2 into 2n pi. Integral 0 to 2n pi cos u du is equal to 1. We have now brought it to a situation where we know what is the value of the integral. So that is nothing but sine u. And I put the limit 0 to 2n pi. Now this is where we need to remember, for n is equal to 1 or n is equal to 2 or 3 or 4, whenever there is a sine of 2 pi, the value will be 0. And once again, sine 0 also will be 0. So if I consider that, this entire term here becomes 0, or this entire product becomes 0. So I will get mod c square into L by 2 is equal to 1, or mod c square is 2 by L, or c is equal to square root of 2 by L. Bring back, substitute it back to the wave function. So wave function now becomes square root of 2 by L sine. It was sine kx. I'm replacing k with n pi by L. So sine of n pi x by L. So square root of 2 by L sine of n pi x by L. This is the expression for the wave function, or this is the eigenfunction. And we notice that for every n, there is a different value for the wave function. So that is why we have put a suffix of n. Psi n is equal to square root of 2 by L sine of n pi x by L. N is equal to 1, you get square root of 2 by L sine pi x by L. N is equal to 2, you get square root of 2 by L sine 2 pi x by L, like that, and so on. So now let me just make you think a bit. I'm going to say that the lowest energy level cannot be 0. It has to be when n is equal to 1. N cannot be 0. How do we now understand this? If n is equal to 0 here in this particular expression for wave function or the eigenfunction, if it's n is equal to 0, what will happen? This entire term, this entire wave function becomes 0. If wave function is 0, that means the particle is not there. It is not existing. That is not a valid situation. We did consider that this particle is there existing inside this infinite potential well. So your condition of wave function becoming 0 inside the box is not applicable. So n is equal to 0 is not valid. You cannot have that particular situation. So n cannot be 0. So the lowest value of n is 1 and never 0. In the case of particle existing inside an infinite potential well. So energy level also will be, the minimum energy level will be when n is equal to 1. So if I bring back that expression for energy, I substitute by n is equal to 1, I will get it as h square by 8ml square. And this energy value is known as 0 point energy. It's called as 0 point energy. It's not the energy is not 0, or n is equal to 0 is not valid, for the reason that when n is equal to 0, wave function becomes 0, or the particle should not exist, and that situation is contradictory to whatever we are considering. Now, I can even find the probability density if I take integral mod psi square dx. All I have to do is take psi and psi star and take a product of them and integrate it. And I will get something like, as a function of, there is an integral over here, 2 by L sine square n pi x by L. So probability is actually sine square as a function of sine square, while wave function is sine. It's a function of sine. Now probability can be maximum when n pi x by L is pi by 2, 3 pi by 2, 5 pi by 2, like that. So depending on the value over here, you will get the maximum probability. Now, yes, I can even consider if there are two adjacent energy levels, say En plus 1 and En, then I can find the energy difference. All I have to do, say for the En, it will be n square h square by 8ml square. For n plus 1, it will be n plus 1 the whole square, h square by 8ml square. Just take the difference and get the difference in energy level. Yes, to an extent I can approximate it. So if I do this, I can approximate it to h square by 4ml square into n. All right, now moving on with understanding how, like the figure which I had shown earlier, how do we represent the wave function and how do we represent the probability, and also obviously the energy values. So as we said, there is no n is equal to 0, so there is nothing here below at this particular situation. There is n is equal to 1, your energy level, the 0 point energy has a particular value. So that is h square by 8ml square. It will be at this energy level. N is equal to 1 will be over here. Now, if I put for n is equal to 1 in the expression for psi of x and probability, I will get the function like this. So this is how psi of x looks like. And this is how mod psi square will look like. Or the probabilities will look like. Because this is sine square, it's a function of sine square. And this is a function of sine of x. Now next you have n is equal to 2. So energy is 4h square by 8ml square. You will end up getting a full sine wave like graph the sine wave like graph for the wave function. But yes, you're taking a square, because of that it will be all positive. Only positive cycles will be there for the probability density. Again, like that for n is equal to 3 and 4 and so on. Now, if you now focus at the probability density, you can see one thing. The minimum probability density is 0, maximum probability density is whatever is the amplitude, say I take it as 1. So there is a minimum probability density and maximum probability density. But also at the same time, there can be probability density somewhere here in between. There are situations in between also. So probability value varies from 0 to 1. It's never like either 0 or 1. It is between 0 and 1, I can say. So somewhere from here, the concept of qubit comes into picture for the present quantum computers. The concept of qubit comes into picture, that 0, you have a state with a 0, you have a state with 1, and also combinations of 0 and 1, because the probability is not just 0 and 1, there are also other probability values existing for the particle. So for that reason, we need to be remembering this particular aspect, and because of this particular aspect, lots of applications come into picture. And so this is just one application of Schrodinger equation, which I have explained to you all now. There are other conditions also, like finite potential well, and what if there are situations in which the particle is able to cross the boundary? What if it's not a well and it is something like a tunnel? The figure is completely in the opposite direction. So there are so many applications. So obviously those who are interested, they can go through other advanced quantum mechanics textbooks. As of now, let me end with this particular application, which was particle existing in an infinite potential well, and where we applied the one-dimensional time-independent Schrodinger equation, and we have got the expressions for the eigenvalue, that is the energy, n squared by 8ml square, and the wave function, that is eigenfunction, psi n of x is square root of 2 by L, psi n of n pi x by L. Thank you very much.